Welcome. In our earlier lecture, we learnt about regression, and there I told you that why we need to do regression to correlate the data, and in those cases we also find that we can use the regression to get the values of some dependent variables at some points which are not given to us. In similar fashion, we also do interpolation. In case of interpolation, we do not need to do any kind of curve fitting, we do not need to know the exact nature, but in this case we deal with still a very limited range of data to find out the values of the dependent variables at some points at some values of the independent variables which are not given to us. Okay, so that is the difference between the regression and the interpolation. So, in this particular lecture, we shall be looking into some very commonly used regression methods, which is again not very exhaustive, because in separate courses on the numerical techniques, you get to learn more about this interpolation, and you are given many interpolation methods. So, here I shall be restricting myself only to two types of interpolation methods. So, first we shall go by the examples, and in that only I shall be explaining to you how those formula have been obtained. So, now let us see that it is a very common problem that we have to find the value of logarithm of 2, that is natural logarithm of 2, using Newton's difference formula, and again you see there are many variations of that, and Lagrange. Now, you see that this ln2 you can find the value easily from any kind of logarithmic chart. Now, we shall see that how do we get to interpolate these values. Okay. So, first before we go to the solution, let us first understand a bit of this interpolation principle. In this we have say n plus 1 data points, okay, and through this n plus 1 data points we can fit a curve of degree n, okay, and that this polynomial fit will be looking something like this, that if we have a polynomial of degree n, then it will look like this. Okay. Now, you can see that all these b0, b1 etc. bn values can be given like this. Again, I am not going into the derivation of these equations. Thing is this, that this particular thing, this in third bracket what you see, this is not representing that it is some unknown function, it is representing some kind of difference function, and how this difference function is obtained we shall see later. Now, here we have the explanations that bxi xj fx, that means that fxi means if fxi minus fxj divided by xi xj. Now, this fxi fxj xi xj, they will be given to you. Okay, and from that you can find this value of this f third bracket x1 comma xj. Then we have xi, xj and xk, and this what it means, that first you take f xij and then you take f jk. So, this is the way you are going to find out this value, and again you see that this f xi xj can be found from this formula, okay, and this also can be found from this formula. Similarly, if you keep proceeding with more and more number of points, you will see that the value of this f, this left hand side, will depend on the values of the f on the one we have found in the previous step. Okay, and this is how we continue. Now, here if you put in a very tabular form, you can see that how it will look like. Suppose you are given 4 points, one is x0, x1, x2, x3, like that. The 4 points are given, and at these 4 points you are given some function values. Now, if you go with the linear interpolation, then you need to find only one difference points. Okay. That means, if you arrange these fx0, fx1, fx2, fx3 like this, and then by taking the difference between, that means this value minus this value will be this, then this value minus this value will be this, and this value minus this value will be this. Okay. Now, you see that this choice of the x0, x1, x2, x3 is generally arbitrary, but when you are doing interpolation, you should not do it arbitrarily, otherwise what happens, that your accuracy of the result will change. So generally what we do, that we generally put these x0, x1, x2, x2 values either increasing order or decreasing order, okay, instead of making it arbitrary, even though this formula can be applied in an arbitrary arrangement of this x0, x1, x2 and x3. Okay. Now let us see that let us suppose that this we have the given curve like this. Okay. Now please understand, this given curve may be the actual curve which we are getting from some experimental data points, or some theory, or this may be a regressed curve also. Okay, that now you see that how the regression is coming to picture, that I can generate this curve either from theory or from regression from some experimental data. And now what we have to do next is that suppose we have to find the value at some point x here, given the points x1 and x0. Okay. Now you can see, if we are doing a linear interpolation, you can see that the value which will be given by this interpolation will be somewhere here, because we are linearly interpolating it. We are assuming a straight line between this x0 and this x1 point, straight line. So this is the value which we shall be obtaining at some unknown value which is lying between x0 and x1. However, you see the exact value at this point is this one. So you can see that depending on the linearity or non-linearity of the given function, this is a given function, the accuracy of the order of the interpolation will differ. So in this case, you can clearly see that a linear interpolation is not giving us a very good result. But anyhow, we shall see that how we are going to go with this linear interpolation first. So this is the formula you can easily find out from the linear interpolation, and let us go about, and we will see that depending on that the range we take for the interpolation, suppose you can take, suppose this is a given function, say log x. So either you can take a very large range or you can take very small range. Okay, and this is the value. Here you have to find the value of the function. So if you take a very large thing, you see that this is the value you find. Okay, so this is where you want to find the value of the function. But if you take this larger range, you get this particular value. And now if you make the range smaller, you find that you have improved the value from this value to this value. Why? Because the error between the actual value and the estimated value is coming down. Okay, so that is what I was telling, that what kind of range you are choosing and what kind of functionality you have, these two will determine the accuracy of your result. So you have to be very cautious whenever you are going to interpolate, that what range you are going to adopt. If you have some understanding of the nature of the behavior of the dependent variable on the independent variable a priori, that means before you start doing the interpolation, sometimes we get these kind of things from the theory itself. Theory tells us that how the particular dependent variable will change with the independent variable. For example, if you want to know that how enthalpy will change with temperature or pressure, how the entropy or the internal energy or density, so all these things, how they will change with the temperature, pressure. If you have some kind of understanding a priori from theory, then you can judiciously select the range for interpolation. Now let us see. Now this we know that if our value is fx equal to ln2, that is given to us, so this is the exact value of the log 2. Now let us first take that we are going for linear interpolation. So let us arbitrarily choose two values of x, and one we choose that x0 is 1 and x1 is 6. Now you see that we have chosen a very large range and our value has to be found at 2. Okay. But nonetheless, let us do that. So we find that from the given value, given ln x, we first put 1 here, okay, and we find fx0 equal to 0. And then what we do, we put this 6 here and find the value of this f6 as this. Okay. Now we apply this formula for the interpolation. Okay. Now we plug in these values of fx1, fx0, x1, x0, etc. And this x we are putting the value of 2. Okay. And now what we find, that after solving you get that this is the value of ln 2 by interpolation. And now you see the exact value was given like this, and this is the estimated value from interpolation and see that we are getting such a large deviation. This is a percentage error we are getting. Okay. Now let us go try out another one. Every time this can be known only if we know the exact value. Now suppose you do not know the exact value, what you should do? In that case, another way is this: you choose some arbitrary range initially. Okay, you find the value of the particular function at the given independent value, and then what you do, you again choose another range. Okay, and you decrease the range by say half. Again you find the value of this particular function. Okay, now by doing again what you do, that you just compare the values you obtain for the function for the consecutive ranges. If you find this is coming almost same, then you can say perhaps any of these ranges would do. Okay, and you can take that to be the right value. But if you find there is a big deviation between these two values, again you go for another smaller range maybe. So in that way, slowly and slowly you keep on changing the range and keep figuring out the relative deviation between the values at two consecutive ranges. Okay, and that way you sort of go to the I don't say right value, but some converged value. Okay. So now what we do, that we go for another range. Here we choose x0 same as previously what we have done as 1, and now we shrink the range to 4. Now again we find the value of f4, that is log of 4, and this is the value. We plug in for this in this formula to find the value of f12, and we find this value. Now please understand here that as I told you that x0, x1 are arbitrary. Okay, so that means you can put this as x0 and this as x12. Okay, so if you put this as x0 and this as x1, you have to make the appropriate changes in your formula. Okay, so this choice of the x0, x1 is arbitrary. Just you have to modify the formula, but whatever you choose, you will find that the values of the interpolated values will be coming almost the same. Okay. So here we have chosen this values of x0, x1, and we get the value of this ln2 at by interpolation here. Now we see, if you compare this value with the exact value, we find now we have brought down the relative error to this, but it is still quite high. Okay, it is still quite high, 48 to 33, it is still quite high. So if you want to still make it more and more accurate, you just keep on shrinking this range, and you will find that after a few iterations you will be able to figure out that what range is suitable to make the interpolation. Now we go to a quadratic interpolation. Quadratic means we shall be now fitting a polynomial of degree 2 to the given values. Now you see that when you talk of fitting a polynomial of degree 2, that means you would need 2 plus 1, that is 3 points. Okay, that from that only you can get a polynomial of degree 2. So here again we consider same thing, that this is the first difference we have found out. Okay, and from the first difference now we find the second difference, so that we can fit a polynomial of degree 2. So again we find this x2, x1, x0 like this, that we are taking the difference between this and this. Okay, and x3, x2, x1 we take the difference between this and this value. Okay, so you can see that it is very easy to do this determination of this difference function if you put them in this tabular form. Okay. Now after finding this second difference, what you now do, that you go to this formula again, and here you find we have this value of b0, b1 and b2 have to find out. Now you can find out the b0 value easily if you put x equal to x0 here. Okay, what you find, that f2 x0, then this is b0 and this is also 0. That means b0 is equal to fx0. Okay. Now what you do to find the value of say b1, what you do, you put the value over x1 here. Okay, once you put x1 here, you find that this will be 0. Okay, so this goes. Now what we left with, that f2 x1 equal to b0 plus b1 into x1 minus x0, and from that you can find the value of b1. Okay, so you get the b1 value as fx1 minus fx0 divided by x1 minus x0. And what fx1 minus fx0? This is nothing but f third bracket x1 x0. So this particular value is nothing but, you can write this is at if x1 x0 divided by x1 minus x0. Okay. So this is how you see that you can use the difference values right from that particular table, and then you go for determination of this B2. For that what you do, you put x equal to x2. Now if you put this x2, what you know, that this x2 minus x0, you know the value of b1, you know the value of b0 fx0, and this is the x2. Now you can easily now manipulate this equation to get the value of b2 like this, that fx2 minus fx1 divided x2 minus x1 minus fx1 minus fx0 divided x1 minus x0 divided by x2 minus x0. What it basically means is this: you are getting this value like this here, this particular thing is nothing but if x2 x1, and this is if x1 x0. Okay. So you are able to get these values. Now let us assume, when we go back to the problem, let us assume that x0 equal to 1, x1 equal to 4 and x2 equal to 6. Now we are taking 3 points to get the value of ln 2. So as usual, that fx0 equal to 0 and fx1, that is ln 4, equal to this, and fx2, that is ln 6, is equal to this. Okay. Now as we have found earlier that b0 equal to fx0, that is 0. So b1, we get the value of b1 like this. Okay. And we get the b2 like this. Okay. And we find that if you plug in the values of this is the value of the f2. Now you see that if you compare this value with the earlier exact value, you find now by doing a quadratic interpolation, we have been able to reduce the percentage error, but still it is quite high, it is still 18%. So we can again play with these ranges. Okay. Now here you have shown that this is this black thing is showing you the exact function. Now what we are doing, that we are taking 3 points. This is 1 point, this is second point, and this is third point. Okay. Now if we are taking linear interpolation, we find that when we do linearly, this is the estimate we are getting, and when we do a quadratic interpolation, we have been able to improve the values. Okay. Now that means for that, by increasing the degree of the polynomial, we are able to have a more accurate value. But you must also understand that as you increase the degree of freedom, degree of the polynomial for interpolation, you also are paying for the calculation. Okay. So you have to be very cautious that whether you should go with higher degree or whether you should stay at a lower degree but keep shrinking the this range for interpolation. Okay. So this has to be decided on case by case basis. Now we go for cubic. Now cubic, now we are going for this third difference. Again you can see that how this third difference is coming. Okay. Now you see here are this is a formula over here, and here we are getting the difference table we are making. So here we have the first difference, that is between these two, and then second difference between these two, and third difference between these two. Now you can see that after making these things, you can again find this divide the difference, you can find out this b1 etc. as I explained to previously. Okay. Now you can find the second divided difference here, then third divided difference here, and these are the values of b2 and b3. Okay. So from these differences, what you find, that ultimately you plug in the values over here directly and you get the value of the function like this. Now what is the thing you have got? You have been able to reduce the error to 9%. Now again you see that now this is the cubic polynomial we have done, and here the estimate has come to still nearer to the exact value, but it is all coming at the cost of the calculation steps. Okay. Now you see that you can now you can go for a fourth order polynomial. Now if it is a fourth order polynomial, you can see that you have to consider another point, that is you have to consider 5 points. Okay. The same thing will be there. Now if you have to have that fourth order polynomial, then what you can do, that if I go back to this difference table, you can see that here you have to have another point over here. Suppose I equal to 4 you put here, then it is x4, then if it is fx4, and then these two will give you that f x4 x3, and then these two will give you f x4 x3 x2, and these two will give you f x4 x3 x2 x1, and then you have fourth divided difference, and this will give you ultimately f x4 x3 x2 x1 and x0. Okay. So you can see, now you can see that this is the way you can proceed with higher and higher degree polynomial. Now how much you should go, that will be decided, that what is the difference in the accuracy you are getting and how much you are paying for the calculation. These two will generally dictate that how much, means which degree of polynomial or which degree of interpolation we should be applying in a given case. Okay. Sometimes we find that many times we do linear interpolation only. It is very popular that we choose a very small range and we get in one iteration only we get the value of the dependent variable at the unknown that some intermediate independent variable value. Now after this, this is a Newton's divided difference. In this case, what we are seeing, that we are taking these differences generally in a very means methodical manner. As I told you that we put the things in a decreasing or increasing order. Another way is this, another formula is by Lagrangian interpolation. Here you see that these x0, x1, x2, these can be chosen arbitrarily. Okay. Again, without going into the detail of the particular derivation, just you understand that this is the way we are putting the Lagrange formula. Here again we have a nth order polynomial. Here we have writing like this, and this L is a Lagrange for polynomial. Here you see that it looks like this. Okay. This is a capital pi. This shows the product. So this product means it is, if you expand this product, it will look like this, that it will be x minus say if x1 divided by x1 or xi minus x1 into x minus x2 divided by xi minus x2 like this it will go. Okay. Now this way it will go on. So it will be here j over here, this is not equal I. Okay. So this it will go, do this slight modification to do. So this is the way it will go on. Okay. Now once you do this, then you find that you can easily find out for the first order. Again you can have several different orders if you take n1, n2, etc. So this is the first order thing you can find out. Okay. And we shall be applying this formula also in our thing. Now this is the second order formula. Again I am not going to detail of these things. So let us first go with this thing that we take, that if you take a second order first order polynomial, if you take it to be this 1, 4, 6, if we take here, so we find that fx0 equal to this coming, and here we plug in the values over here and we get this value of the thing ln 2, and this is the first second order polynomial. You can easily see that our value was some 0.61 something, and it is we are getting by first order we are getting 0.46, and by second order we have improved to 0.56. Okay. So that means what we are finding that in this Lagrange also we are able to get a better value if we are increasing the order of the polynomial, and similarly we can keep on going for higher and higher order using the Lagrangian formula. So these are the books which you can refer to for further explanation on these theories.